So in this lecture, we're moving on to a network of Hindmarsh-Rose neurons, in particular a ring network. So just to refresh your memory, a ring is essentially a cable that folds back on itself, and the topology of that network is defined by a banded connectivity matrix such that each neuron receives input from its neighbors to the left and to the right, but no others. Okay, so we proceed in the toolbox much as we did in the last lecture. We look at the Hindmarsh-Rose script, and in this case I'm going to use the prearranged example here to construct a network of 20 neurons. So here's our Kij, the banded matrix which defines the ring topology, and this whole script here I will just run holus bolus using the evaluate selection option in Matlab and wait for it to start up. Make the window a little bigger. And wait for that to come. Alright, so you can see our banded matrix up here in the control panel. You can also see that our X, Y, and Z state variables are now vectors. So they are each vectors of size 20 by 1 row. So there's one value for each neuron in each of these state values here. Now our injection current I is also a vector in this case, so we have a unique injection current for each neuron in the ring. So let's have a look at the time portrait. The time portraits show all 20 the time portraits for X show all 20 neurons superimposed. Same for Y. We can switch to Z down here, and we can choose the particular neuron that we want to look at by unchecking this checkbox here. So now we're looking at the first neuron, X1. We can switch that to X2, X3, X4, and so on. Let's look at X10. And just for comparison, I want to look at X11 in the bottom screen. So we'll make that one X11. Okay, just put those, check those boxes back. We can get rid of the phase portrait because it's not much use in this case, so I'll just close that. And the space-time plot. Now this is more useful. So here we have space along the vertical axis, so the first neuron is up the top and the last neuron is down the bottom. Time runs along the horizontal axis. And we can see that all our neurons begin with random initial conditions. So if I randomize all of the initial conditions again, or re-randomize them, we'll get a different simulation run. And again. And we can see those results also in the time portrait, running again with new random initial conditions. Now let's return to the Hindmarsh-Rose equations, and remember this network input term. Well, that vanished when we were looking at the single neuron, but now it has an impact. It represents the net input to the ith neuron from the other neurons. In this case, because our connectivity matrix is banded, that just means each neuron receives input from its neighbors to its left and neighbors to its right. And the strength of that connectivity is governed by this scalar GS, which represents the synaptic conductance. So if we increase that synaptic conductance between the cells, we ought to see them start to synchronize. So here's GS here. I'm just going to click it up on a level and see what happens to our simulation. Alright, so now we can see all the neurons start to simulate. Not simulate, start to synchronize. If I randomize initial conditions, you'll see various incarnations of traveling wave solutions, where the traveling wave is a traveling wave of bursts. It's a traveling burst, so you can see the burst here. Okay, now let's change our injection current to just a couple of cells. So I'm clicking on this button for the I parameter, and it brings up this dialog box for editing the individual values in that vector. So here are the values here. You can also look at the histogram and the statistics, but that's not much use to us at the moment. What we want to do is fill all those values with 0, so I can put 0 in that fill value box, and that will be applied to all the elements of the injection current. Now that we have no injection current, the network ring will fall silent. I'm going to choose the middle neuron, which is 10, neuron 10, and just apply an injection current to him alone. And you can see that that single neuron starts to burst. We can look at that in the time portrait. Okay, neuron 10 is bursting, and the other neurons are quiet. Let me also apply that to neuron 11. So now I'm going to stimulate neurons 10 and neurons 11. You can see them both bursting now. Switch back to the time portrait, and we can see those neurons burst, and they start to emit little traveling waves out to the side which don't quite propagate around the ring. So I'll get rid of that, and let's just play with our synaptic coupling strength, GS. So if we increase the coupling further, we should see traveling waves that travel in both directions away from the stimulation site, and they actually encounter each other at the far side of the ring and annihilate one another. We can evolve that solution to get rid of those initial conditions and see the steady state behavior. Let's run that again, and you'll see these waves emitted from the stimulated neurons traveling in both directions around the ring, where they encounter one another and annihilate. So if I increase GS a bit further, we'll see those waves travel even faster. Okay, so remember, they're waves of bursts. Now if we reduce that synaptic coupling, we'll see the wave speed slowing down, and ultimately, got some intermediate effect there. I'll just run that again, re-evolve that by clicking the run button. If you want to run a few extra runs, just click that run button while we have the evolve solution, the evolve tick box on. Yeah, so keep reducing GS, and we see now the system is effectively uncoupled. So let's find the critical point where that wave is initiated. If I try point 4, I'll see some funny stuff where waves are emitted every second, or sometimes every beat of that, or every burst I should say. I can run that again. And you get some weird stuff happening there. If I increase up to 0.5, that alternating wave should go away and return with the persistent wave on every pulse. Back to 0.3, and the wave's gone. 0.35. That's the emission. There's a slight wave emission there. It's not quite taking off. 0.36. Getting a bit bigger and now alternating in direction. 0.37. Oh, no, that's 0.36. 0.37. Getting a bit bigger, I think. 0.38. Yes, we're definitely growing. 0.39. So we have waves that travel a short distance and now we have waves that travel all the way out to the other side of the ring. But in this case, they only emit on every second burst of those stimulated neurons. All right, so what happens if we take GS down? Oops, gone too far. Let's take down to, well, 0. I clicked that too much. I'll just run that again. Getting ahead of myself. Okay, 0 coupling. This is an uncoupled system. Now let's go to negative coupling. What might that do? 0.25. All right, so we see that with negative coupling or inhibitory coupling, the two stimulated neurons start to synchronize in antiphase. So I'll just continue that run again. So we can see antiphase behavior arising from inhibitory local coupling. I'll just decrease or go more negative with that inhibitory coupling and see what happens. 0.75 minus 0.75. Okay, so you see that the two stimulated cells are remaining in antiphase, but we're seeing some effect bleeding out to their neighbors. Let's take it down some more. -1. More bleeding out into the non-stimulated neighbors of the ring. Bring it down again. Let's go -1.5. And that effect is that bleeding out effect, I call it, is reaching further and further into the network, extending further away from those stimulated cells. So let's just bring it down even more. Go a bit mad. Take it down to -4, and we can see some spikes starting to emerge in cells that are not even stimulated at all. If we switch over to the time portrait, we can see the antiphase behavior of those cells. Let's go -5. And we see that alternating bursting behavior starting to encroach across the entire ring, which is very counterintuitive, but it happens. Whether it happens in biology or not is another thing, but here in the model we see that strong inhibitory coupling can evoke a signal that propagates away from the site of stimulation, which is probably not what you would think intuitively. But anyway, you can play with these sorts of things forever, and of course I encourage you to do so. So at this point, I think it's time that you try to do this yourself and get the hang of simulating a network.